When did the universe begin? How did it begin? These are questions often pondered by cosmologists and everyday people alike. It doesn't matter when or where you come from. At one point or another, you've probably caught yourself wondering these same thoughts too, which we will be exploring in this video. This is the beginning of our universe. Wait, where are we? Whoa! This must be the Big Bang, theorized to have taken place approximately 13.8 billion years ago. This is the most widely accepted viewpoint on how the universe is thought to have all begun, known as the Big Bang Theory. Yes, you heard that right. As a theory, this is our best guess as to how the universe may have begun, and there are other theories pertaining to the origin of the cosmos, but let's save that for later. The Big Bang Theory suggests that this cosmic explosion took place on an infinitely small, yet infinitely dense and infinitely hot point called singularity. These numbers are beyond our current abilities to measure and comprehend, among other factors that make trying to replicate a miniaturized simulation of this event in its entire splendor near impossible. But alas, scientists have been able to gather quite the detailed picture of what became of our universe mere moments after it is believed to have begun. Now, before we begin this cosmological journey through our universe's beginning, we need to understand something about the nature of the cosmos, which is the four fundamental forces that govern every physical process that creates change in everything around us. These four forces are gravity, the weak nuclear force, electromagnetism, and the strong nuclear force, all of which were hypothesized to be one cosmological force at the beginning of time. Scientists coined this term to be a grand unified theory, or GUT for short. The strong nuclear force, the most powerful of the four, is responsible for holding together quarks, which are subatomic particles that make up the protons and neutrons of the atomic nucleus, the things you see everything is composed of. The strong nuclear force also holds together protons and neutrons that form atomic nuclei. Without it, nothing even remotely visible would exist, and the universe as we know it would simply be a scattering of particles and energy. No stars, no planets, no galaxies, nothing. The second strongest force, electromagnetism, is responsible for all the interactions positively and negatively charged particles have amongst each other, as well as also controlling magnetic and electromagnetic fields. The reason we see is due to photons, which is in the form of electromagnetic waves, reaching our eyes as visible light, creating a picture within our minds. Without electromagnetism, the universe would be a lightless, colorless mesh of matter that would be virtually invisible to any sort of optic. Next comes the weak nuclear force, which is responsible for the process of nuclear fusion, allowing stars to emit light and energy over the course of billions of years. The weak nuclear force also enables radiation and the decay of unstable particles to take place. Lastly, but certainly not least, is gravity, the force we're all most commonly familiar with, which peculiarly enough happens to be the most puzzling fundamental force of the four. Responsible for the motions of all objects throughout the curvature of space-time, gravity is thought to have broken off from the fundamental forces first at the beginning of time, making it the weakest of the four. However, it did so at a time we do not yet understand due to the extremities of the environment. From when the universe first began at time 0 as a singularity, to 10 to the negative 43 seconds. That's a decimal point, followed by 42 zeros and then a 1, is known as the Planck era, to which we have no idea what happened during this time. The most dramatic changes to the cosmos are thought to have happened not even a minute into reality thus far. From 10 to the negative 43 seconds to 10 to the negative 33 seconds, gravity is thought to have broken off from the other fundamental forces. Immediately following that, to about 10 to the negative 30 seconds, was the epoch of inflation, in which the universe expanded by a factor of 10 to the 26. This is the equivalent of taking a monkey and expanding it to the size of 1,000,000 Milky Way galaxies. This idea of an unimaginable expansion during an extremely short period of time helps explain why our universe is so smooth and uniform in terms of temperature and matter distribution, to which we believe this occurred due to the presence of an unknown entity called dark energy. Almost instantaneously, all matter and antimatter became spread out across the expanding cosmos, with matter dominating over antimatter. This is believed to be due to quantum fluctuations that must have created slightly more matter than antimatter particles, on a scale of 1,000,000,001 matter particles for every billion antimatter particles. And since matter and antimatter annihilate each other when they collide, antimatter would become scarce in our universe. Simultaneously, with temperatures and the density of the universe rapidly decreasing, the remaining unified forces began to separate, and the cosmos became fundamentally changed forever. Fast forward to a 3-minute-old universe, and the cosmos has finally cooled enough to the point where subatomic particles could form into protons and neutrons, creating heavy yet stable isotopes of the first 3 elements of the periodic table we know today: hydrogen, helium, and lithium. This process is called nucleosynthesis, which is the formation of atomic nuclei from baryonic matter, protons and neutrons. Prior to now, such atomic nuclei were unable to form due to being blasted apart by high-energy photons at hotter temperatures. However, at this point in time, these atomic nuclei were not neutral in charge, as the universe was still too hot for atomic nuclei to snag electrons, meaning in addition to the entirety of the universe being composed of hot ionized plasma, there was also an abundance of free electrons spread out throughout the universe. This caused photons to scatter inescapably and endlessly off positively charged atomic nuclei and free electrons holding a negative charge. By this condition of the cosmos, the universe was so bright with all the scattering photons, it was opaque with a thick and foggy white light. This all changed when the universe was about 380,000 years old, known as the era of recombination. Since the cosmos was ever expanding by dark energy, energy could continuously be dispersed, cooling outer space by this point to about 3,000 Kelvin, which allowed for atomic nuclei of hydrogen, helium, and lithium to snag free electrons, creating electrically neutral atoms. This put an end to the scattering imprisonment of photons, allowing light to travel and disperse freely, causing this time period to be the oldest in which we can observe light, when it began traveling in the manner we know it does today, unimpeded and universal. You may have seen this image before. This is the earliest light we were able to detect when photons were first able to travel freely, in which we call this cosmic microwave background, or CMB for short. Directly following this, when all the light of the cosmos was finally able to travel freely, came a period known as the Dark Ages, in which the entirety of the universe was pitch black and transparent, with not a trace of light to be seen. This was a time when the universe was mainly clumps of neutral hydrogen, scattering about and slowly becoming more concentrated as gravity attracted larger clumps together. Eventually, after several 100 million years passed by, gravity would have brought together enough dense concentrations of hydrogen for the first stars to form, bringing an end to this cosmological darkness. It is now the epoch of reionization, with new light spotting the universe as extremely massive stars formed out of darkness, which were thought to be anywhere from 30 to 300 times as massive as some of the largest stars we know today. With such extraordinary sizes, these stars only burn for a few million years before exploding in a supernova, in which it is thought that these stars would set the precedent for forming the supermassive black holes that we now find at the center of almost every galaxy in the universe. Stars can no longer form in the magnitude we see at this point in the cosmos, and was only thought to be possible due to the conditions of the universe in terms of density and temperature, causing a greater pressure on these stars, allowing for the larger sizes to be sustained. More importantly, however, was supernovae on a scale we've never seen before. The ultraviolet light that would be energetically released from such explosions was strong enough to tear apart neutral atoms, turning them back into protons and electrons. This process is called ionization, and is the reason we call this essential point in time the epoch of reionization. The universe is now 1 billion years old, and with the continuous rise and fall of supermassive stars and supernovae, the first galaxies began to form in the ever-expanding universe. Over time, the cosmos would be scattered with clusters of galaxies, stars, asteroids, and much more, as the explosions of stars created the elements well beyond just the first 3 on the periodic table, bringing rise to matter of new shapes, sizes, and forms. The universe would become changed forever, as it no longer was a distribution of plasmic hydrogen, but instead one of a vast yet diverse composition of matter, one that was beginning to look a lot like the one we know today. Over time, dark energy would continue to expand our universe at an accelerating rate, cooling a 13.8 billion-year-old bubble of space into one with a temperature of 2.7 Kelvin, and full of worlds peculiar like this one, where we will pick up on in the next video in this series, where we'll explore the curious nature of objects we observe throughout our universe today. Now, before we bring this first video to a close, there is one more thing we must discuss about beginnings that we glossed over towards the start of all of this. This entire video so far has just been about the Big Bang Theory, by far our best guess as to how the universe came to be. But, with the Big Bang Theory not yet factually proven to the point of no doubt, this leaves room for speculation and other guesses to emerge about the nature of the cosmos that are also in the realm of possibilities. One of these is the Milne model, which bases its proposal on complex mathematics and Einstein's theory of special relativity. More info on this will be found in the description below. There is also the oscillating universe theory, which states that our universe goes back and forth between expanding and shrinking, that our universe exists in cycles in between a Big Bang and a Big Crunch. We will discuss potential ends of our universe in a future video in the series, but in simpler terms, a Big Crunch says that the universe will come to a point where it will stop expanding due to the density of the universe and gravity becoming large enough to overcome the expanding force of dark energy, and that the universe will begin to collapse until everything is back to the way it started, a singularity. All matter is compressed back into a single point in space. From here, the universe is thought to restart all over again, with another Big Bang, followed by another Big Crunch, and so on and so forth, condemning the cosmos to an endless cycle of expanding and contracting for all time. This would imply that the universe as we know it came from an unknown number of cosmological oscillations before it, which we would have no knowledge as to how many iterations of our universe there have been. So although the oscillating universe theory doesn't necessarily propose a new cosmological hypothesis on the very beginning, it does add on to it by stating something else came before the Big Bang of our current universe. Our next hypothesis comes from the steady-state theory, which originally was the most widely accepted theory of the beginning of the universe before the Big Bang rose in popularity. The steady-state theory suggests that the density of all the matter in the expanding universe remains constant due to the continuous creation of matter at a rate of 1 hydrogen atom per cubic meter per every 100 billion years. This in a sense also renders the cosmos uniform, no matter what time or place you observe. It states that the universe has no beginning and no end, and that the universe steadily progresses to no foreseeable finiteness. Although this theory was largely disproved with the discovery of the cosmic microwave background in 1964, this idea is still modernly adjusted to try and account for new scientific discoveries made in the present day, and is now known as the Lambda Cold Dark Matter Model, or LCDM for short. Our last cosmic origin hypothesis we'll be covering in this video is another add-on to the Big Bang theory, known as the Hartle-Hawking state, which describes a case where there is no true beginning or end to the universe. Instead, before the Big Bang and before the beginning of time itself, only empty space existed. This theory describes a reality where the universe quote-unquote began with no element of time at all. So although the universe and time had a definitive beginning, by this hypothesis, space did not. The universe was originally empty, timeless space that due to quantum fluctuations prior and or during the Planck era caused time and matter to come into existence with the Big Bang. This no-boundary theory also describes a situation in which the entirety of the cosmos can be predicted by some universal wave function, an elegant proposition that allows for the heavens to be simply derived and predicted from a solely mathematical conception. Now, although this sounds great in theory, as we've seen with all these theories, it has its shortcomings, as not only has this cosmological formula not yet been discovered, but also such a thing would predict other potential models of the universe that are just downright impossible and mathematically broken. All in all, we've taken a great leap into learning more about our origins of the cosmological past, and yet we've only scratched the surface in this series. I hope you've all enjoyed the beginning of this series, and stay tuned for more to come. Thank you for watching. We covered a lot of content in this video, some of which may be subject to change as technological capabilities continue to advance in the future. There were several topics such as dark energy, singularities, relativity, and subatomic particles that were not explained super in depth for the sake of clarity on the main focal point of this video, which was discussing the probable beginning of our universe. However, these topics will be properly explained in their own respective videos in the future. Thanks again for watching. If you enjoyed this video, please consider liking and hitting that subscribe button with the notification bell on. If there are other ideas you'd like to see covered in a future video, please leave it in the comments below. Have a great day, and remember to stay curious.